Okay, welcome back. We're still talking about the terminology associated with graph. So we just finished talking about connected. So a connected graph is one where I could find a path to every single node, but I kind of have to be picky in which one I start with. Acyclic, A meaning not, so no cycles. So let's just envision a deep downtown, perfectly rectangular grid system. Can I start my car over here in the corner and turn left and turn left and turn left and turn left and end up at the same spot? Well, of course I can. So is a downtown map acyclic? No. No, it is not. And then there's a thing called an unrooted tree. Unrooted tree. So an unrooted tree is something that is acyclic and connected. And what that basically means is, there's a diagram coming up in a minute where there's two chunks of a map and they're like separated by one thing, like you got a bridge between two different cities, okay? There's only one bridge that connects the two. And so if I want to go from here to here, I'm pretty much guaranteed to go in the middle, right? Okay. So we're going to show that one in a minute. Okay. So on page 237, they talk about the data structures that are used to describe the nodes and the edges, right? I need to have something that shows me where the nodes are, and not necessarily in two-dimensional space, right? And these are just could be an array of nodes, as long as I know the costs associated with them. So there's two major techniques. One is what's called an adjacency matrix. I'm going to show you one. So an adjacency matrix is just a two-dimensional array showing how this thing works. And just hang on, we'll get there. And so I can get from 1 to 2. Now, by the way, these are not weighted. So here, 0 means I can't get there. 1 means I can get there, but I don't care how long it takes to get there. So can I get from 1 to 2? Yes. Can I get from 1 to 3? Yes. Can I get directly to 1 to 4? Not directly. Can I get to 1 to 5? Not directly, no. So this is the adjacency matrix. It tells me this is where are my nearest neighbors, okay? From 1, who are my neighbors? Well, from 1, my neighbors are 2 and 3, and that's it. From 2, where are my neighbors? Well, 1, 3, and 4. For 3, who are my neighbors? 1, 2, and 5. See, I find this easy to comprehend. I kind of look at it. Now, I'll confess, if you had an awful lot of edges, well, let me just read. Had a bunch of these guys, either both edges and nodes. You can kind of see there'd be an awful lot of zeros in this thing, right? And you could say that this was a space complexity issue because you had to have this monstrously huge set of nodes and how they connect, and with lots and lots of zeros in it. But quite frankly, I don't really care. So yes, there could be lots of holes and a little bit of space complexity, but not enough to be worried about. Now the other technique is to use what's called a linked list. Okay, using the linked list idea is I'm at 1 and I could go to 2 or I could go to 3. And then if I'm at 2, I could go to 1. Now this looks like it's pretty straightforward about, the path I can take to get to each one of these things. I just find it a little more confusing to deal with. So this is more efficiently stored because I don't have to store zeros, right? Okay, good. And it's perhaps a little bit more, this might be a little bit more difficult to discover the edges. Okay, I'm just saying. And dealing with weights here could get a little bit more complex. So on page 237, they go back to showing this guy. So in 237, they show a two-dimensional array, and it's got lots of holes. All the values are 1 because we're not using any weights whatsoever. So, pretty straightforward. The adjacent one, this has a one-dimensional array of linked lists. of the size of the node count. So if there's 5 nodes, then there's 5 of these guys. Each one of those is a linked list. And if you guys know what a linked list is, right? I mean, in theory, you've taken the data structures course, and maybe you've gotten languages where you have like an array list where you can insert something in the middle or pull something out. It's a lot more easier to deal with insertion and deletion if you're using a linked list than it is if you're just using an array. Because there's no way to insert something in the middle of an array and scoot it over very elegantly. But with a linked list, that's pretty easy to do. So building these linked lists is not difficult, but it's an array of linked lists. Or you could say it's a linked list of linked lists, but hey. Okay. So I'm not going to review the linked list thing. I assume you know what I'm talking about. There is a hyperlink in the lecture notes if you wanted to go look. So which of these techniques should I use? I mean, is there one advantage over the other? Well, if you have some issues with space complexity, well, okay. If so, then use the linked list. If you don't have issues with space complexity, I would probably stick with the adjacency matrix, mainly because it just makes the coding so much easier. So, since we're in a classroom environment, we're not really trying to do this in a professional environment. I'm trying to give you the option that's easier to program. And so, yes, using the adjacency matrix is going to be easy for you to write algorithms for. Okay, so that's the reason why we're using algorithms. Not because it's the best, it's because it's the easiest for you to comprehend and be able to write algorithms for. Okay. So, on page 239, they start talking about depth first and breadth first traversal. So before we start, what the heck does traversal mean? Traversal means I need to visit every single node. Okay, now there's a couple of analogies here. Let's say that, I don't know, that you're a traffic inspector and it's your job to go to every single road intersection in the entire city and, I don't know, do traffic counts or something. Okay? That's your job. Well, you need to visit every single node, every single intersection, and you don't really want to visit the same one twice, right? That would be kind of dumb. Like, I've already been here. Why am I doing traffic counts a second time? So your goal is to hit them all with having no or the fewest number of backtracking, right? Okay? So generally speaking, there are 2 techniques to do this. So we already talked about 2 techniques for storing. Now we're talking about 2 techniques for traversing. The 2 are not related. Okay. So, one more time. When I say I need to traverse every node, does that mean it's going to be the shortest distance? No. Okay? It just means I hit them all. That's all. That's all it means. Is it the most efficient way? No. That's not what we're doing. What we're doing is I need to hit them all and not have any duplicates if possible. Okay? That's the goal of traversal. All right. So, if I want to visit every single road intersection just once, then I need to have some way of kind of remembering, so to speak, which intersections I've seen and which ones I haven't. Wouldn't that be kind of cool? I mean, it's okay to pass through one you've been to, but I don't want to stop at a node. Okay? Good. So, the 2 techniques are depth first and breadth first. Now, I'm going to give you yet another analogy, and that is mowing your grass. Okay, you got a little push mower, and you got a perfectly rectangular yard. You could stay at the same level and mow your grass like this in a spiral, right? And then when you got back to the starting point, you decrease the level 1, doink, and then you do another little spiral. And then you decrease the level again, doink, and you do another little spiral, okay? That would be, which one is that? Is that depth first, or is that breadth first? That would be breadth first, means do everything you can see from your current location. Now, let's go back to the analogy of a traffic engineer. I start at one particular intersection, and what I do first is I go to every intersection that I can see. I'm standing in the middle of the intersection. I go, well, I see one over there, and I see one over there, and I see one over there. That's what I'm going to do first. and then I'm going to move. Okay? So that's like mowing the grass. Depth first is, I'm going to go all the way down this street and then come back and then go to all the way down the street until it comes to an end. So in the grass mowing analogy, it'd be like a zigzag. I'd start here and I'd go all the way to the end of the yard and then scoot over one, go all the way back, scoot over one, go all the way back, like kind of in a zigzag pattern, right? So one kind of looks like a spiral where I stay at the same level and do everything I can at that level before I change the level. You know, the other is, I don't care about what level, I'm just going to sweep back and forth, back and forth, back and forth until I get them all. Okay, so those are the two different techniques. And so let's look at what one of these things look like. So here is their example. The order of the depth first traversal would be, okay, they're saying 1, 2, 3, 4, 7, 5, 6, and then now I had no choice but to back up. 8, and then how the heck do I get to 9? That one looks a little funky. I have to go back through, I think they made a mistake here. Anyway, it means, depth first means go all the way to the end every single time. All the way to the end. I want to go from 1 to 9. That's my goal. Go to 1 to 9 every single time. Breadth first means give me all the guys in this current location. So 2 and 8 are really, really close, right? And then close to that is, it's 3 and 7 are pretty doggone close. And then, 4, and then I can, 7 and 4, and then I can get 5 and 9 and 6. So these are just separate techniques to get you to hit all of the items. Now, having said that, one is like a spiral, and then one is like a sweep. Okay, cool. One more time. Both techniques have a starting node, and then you get to see all the rest of them. So one of the things you can do with a traversal is to find out if you have a complete graph. A complete graph means I can get to every single location, right? There's no dangling nodes out there that you can't get to. So one way to do that is to fire up traversal, count the number of nodes you can get to, and compare that to the number of nodes you got. Hey, I can get to 12 nodes. Well, too bad, you have 13. Darn. So a good task for a traversal is to find out, hey, do I have a completed graph? Okay, that's a good tool for doing that. Okay, so does it matter which storage option I'm used to be able to do this traversing? No, not really. So depth first means, again, let's just, I know I'm kind of beating this to death, but just bear with me. Depth first means I start with the first path and follow it until it goes all the way to the end. And so there's some very, very strange pseudocode on page 241, which clearly they don't intend for you to actually implement. This is very, very pseudo code, where I visit a node and I mark it that I have visited it. Because remember, it's okay to pass through it. I just don't want to stop. And then for every edge in G, and so the other one is that you're using a queue. And so where I NQ and DQ, hey, you're making me hungry. So it's kind of sort of similar, except it uses slightly different. So depth first typically uses recursion, where I just run this thing over and over again. So remember how recursion works. Recursion just puts things on the computer stack, right? Okay, we're coming up on the 15-minute mark. You guys know how this works.